Hi everyone. Today we're going to focus on equilibrium. All right, so all chemical reactions, as we've seen, can go in a forward direction, but they can theoretically also go in the reverse direction. So products, which are usually located on the right-hand side of the arrow in our chemical reaction, those can react to form reactants, which are usually located on the left side of the arrow. Now, in order to indicate that a reaction can go in both directions, we're going to use a double arrow. And that double arrow will show that yes, reactants will form products, but also products could reform reactants. All right. So down below we have an example chemical equation where hydrogen is reacting with iodine, and those are both diatomic molecules, and those are going to produce hydrogen iodide or hydroiodic acid. So there's a couple different names for that molecule there. So I'm going to represent hydrogen in black, and then I'll represent iodine in, let's say, blue. And iodine is a bit bigger in size, so I'll try to represent that here. All right. So let's say initially we just have I2 and H2 present in our reaction flask. Okay, and let's say they react and form some product. So we'd have a mixture of atoms here. So we'd have a hydrogen bonded to iodine, and let's say we have another one over here. Okay, so those are our products. Now, the products could actually break back apart and reform reactants. So maybe these two collide with each other and they reform I2, and maybe these two collide with each other and reform H2. So this reaction can actually go back and forth. And most reactions can. It just depends on how much energy you have to input. So sometimes a reaction might typically just go in the forward direction, but if we put in enough energy, we can force the reaction to go back the other way. All right, so there is a reaction rate associated with both of these directions. So when the reaction rate toward the right, so toward the products, is equal to the reaction rate toward the left, or toward the reactants, the reaction is said to be in a state of equilibrium. So that doesn't mean that the concentration or the amount of reactants and products is the same. It just means that the reaction has stopped moving overall in one direction or the other. So what we can do is we can label the rates of reaction for both. So K1 equals the rate of the forward direction, or the forward reaction, and K2 equals the rate of the reverse reaction, where HI is becoming H2 and I2. So when K1 and K2 are equal, then we have reached equilibrium. And again, really important point here. The amounts of reactants and products could be very, very different. The only way that we define equilibrium is if the rates of the reactions are equal, not the concentrations or amounts. So down below are a couple of graphs showing these rates for the forward reaction and the reverse reaction. So when a reaction is in a state of equilibrium, the concentrations of reactants and products remain constant as time passes. Now again, they might not be equal to each other, but they just don't change anymore. So those unchanging concentrations of reactants and products in a reaction at equilibrium are called the equilibrium concentrations. So on the graph on the left, we have a plot of reaction rate versus time. And time is on the x-axis. And you'll notice that initially the forward rate of the reaction, so we're going towards products, is really, really high. But then as time goes on, we start to run out of reactants, so the rate will slow down because we don't have as many collisions occurring between reactants anymore. So this rate is decreasing over time. Now, as the reaction is progressing forward, we are starting to see some products form. So maybe we'll start to see the reverse reaction occurring. So initially, the rate of the reverse reaction is 0 because we don't have any products initially. But then once the amount of products increases, then the rate of the reverse reaction will also increase. And then eventually, both rates will equal each other and we'll have a plateau there. And so that's where those reaction constants equal each other, so K1 and K2. Now on the right-hand side, we have a plot of concentration on the y-axis versus time on the x-axis. So again, initially, let's say we just start out with H2 and I2. So there's some amount of both there. And again, once the reaction starts to proceed, the concentration of those reactants will decrease, and we'll start to see some product forming. So initially, the amount of product is 0, but as the reaction progresses, we start to see the amount of product increase. And then at some point, the concentrations of the reactants and products will stop changing. So that's this point, this dashed line. So this has leveled out the concentrations of reactants and products, and that's when we've reached equilibrium. So those concentrations are no longer changing. Now, the position of equilibrium is an indication of the relative amounts of reactants and products that are present at equilibrium. So we can kind of look at the ratio of how many products do we have at equilibrium and how many reactants do we have at equilibrium. And so that will tell us, which side of the reaction is favored. Do reactants like to form products or do they not like to form products? How spontaneous is the reaction? So the position is said to be to the right when the amount of product is significantly more than the amount of reactant. So if you have a bunch of product, that means the reaction likes to go in the forward direction. So let's say we have a reaction of A plus B, and then it's becoming C. So let's say this reaction loves to produce products. We could even draw the arrow going in the forward direction as being really long to indicate that that is the favored reaction. But we can draw a little baby arrow to show that the reverse reaction isn't as favored, so it doesn't really occur to a significant extent. So again, when you have a ton of products, so C, then that means the reaction likes to go towards the right, or the position of equilibrium is towards the right. Now, the position is to the left when more reactant is present than product. So maybe A and B don't like to react. So we can draw a baby arrow going towards the product to say that that reaction doesn't proceed to a significant extent. But we can draw a really long arrow to show that C loves to decompose into A and B. And this also shows that the position of equilibrium is to the left, towards the reactants. So really here we're just kind of showing which direction is favored. Is the forward reaction favored or is the reverse reaction favored? And it really just depends on if you have more product or more reactant after the reaction. All right. Now we can represent the position of equilibrium in a mathematical way by using the concepts of what's called an equilibrium expression and an equilibrium constant. All right, so let's say that we have a hypothetical reaction at equilibrium. So A and B are reacting to produce W and X. Or maybe the reverse reaction is occurring. We'll find out. So in this expression, these lowercase letters are representing the coefficients of the reaction. So those are our balanced coefficients. And then the uppercase letters are the actual molecules that are reacting or being produced. Now, using that same equation or reaction, we're going to write out something called an equilibrium expression. So the equilibrium constant is that K right here. That's our equilibrium constant. And the equilibrium constant, we could also write that it's equal to the concentration of, whoa, that's a tiny c, concentration of products over the concentration of reactants. So really, we're just, again, looking at a ratio of products to reactants in order to figure out, do we have more products or do we have more reactants? And where does the position of equilibrium lie? Is it to the left, towards reactants, or to the right, towards products? So what we do here is we represent concentration in brackets. So the brackets stand for molar concentrations of the reactants. So all of the concentrations are assumed to be in moles per liter. All right. Now, in the numerator, again, we have the concentration of products. So again, those are represented by brackets. So we have brackets around our first product, W, and brackets around our second product, X. And then in the denominator, we have our concentration of reactants. So we have brackets around A and brackets around B. But you'll notice that each of those concentrations or brackets are raised to a power. And that power is equal to the coefficients that are in our balanced chemical equation. So W is raised to its coefficient of lowercase w, X is raised to its coefficient, lowercase x, A is raised to lowercase a, and B is raised to lowercase b. So we do take into account the stoichiometric ratios, but we're using them as a power instead in this expression for equilibrium. Okay. So let's practice writing out an equilibrium constant expression for the reaction shown here. So we have 2 moles of nitrogen monoxide, and they're reacting with 2 moles of hydrogen gas, and we're producing nitrogen gas and 2 moles of water as a gas, so steam. So again, remember this equilibrium constant K is equal to the concentration of products over the concentration of reactants. And we also want to raise those to the coefficient as a power. So let's start with products in the numerator. So we'll start by putting brackets around N2. So again, the brackets represent moles per liter. So I'll put that up above. And N2, or nitrogen, doesn't really, it doesn't have a coefficient, or its coefficient is 1. So we'll just leave it as it is. We don't have to write 1 up there. And then we'll put brackets around our other product, H2O. And that has a 2 in front of it. So we want to raise this concentration to the power of 2. And again, that's to take into account how many moles of product we're ending up with. All right, and then we're dividing by the reactants. So we have NO, and we'll raise that to the power of 2 because its coefficient is 2. And then we have the concentration of hydrogen. And that's also raised to the power of 2. Okay, so again, this is just showing the ratio between products and reactants at equilibrium. So this K value is our equilibrium constant. And that is telling us the ratio of products to reactants at equilibrium. All right, so we're assuming that this reaction has already finished and the forward reaction occurred, the reverse reaction occurred, and at some point their rates equaled each other, and the concentrations of the reactants and products stopped changing. All right, so let's do a practice problem where we calculate the equilibrium constant for this reaction. So what is the value of K if the concentration of nitrogen monoxide at equilibrium is 0.1 moles per liter, the concentration of hydrogen gas is equal to 0.1 moles per liter at equilibrium, the concentration of nitrogen is 0.2 moles per liter, and the concentration of water is 0.25 moles per liter at equilibrium. All right, so I'm going to write all of the concentrations below each reactant and product because that's easier for me to visualize instead of having to kind of fish through all the information again later. Okay. And then we already wrote out the equilibrium constant expression, so we'll rewrite that. And remember, it's products over reactants. It's very easy to accidentally flip those. Okay, so we're going to plug in the concentration for N2. And I'm going to leave out the units here because typically the concentration, or sorry, the equilibrium constant, very tongue-tied today, typically K doesn't have units. We tend to kind of leave the units out because otherwise we end up with some very strange units. So So don't worry about units for this equilibrium expression. Now, in other cases, units are very important. So don't start leaving out units altogether. It's just for the equilibrium constant. All right, so we don't have to raise that concentration to a power because N2 has a coefficient of 1. But for the concentration of water, we do want to square that. And then in the denominator, we have 0.1 squared times 0.1 squared. Okay, so then we can simplify this to make it easier to calculate. So you could go through and calculate the numerator and then the denominator, and then you can divide those two values. So if you want to pause the video and figure out what K is equal to, feel free. So when I plugged this into my calculator, I got a value of 25. And I think my math was correct, but you can always let me know if I did something wrong. So equilibrium constants can have a wide range of values. It just depends on that ratio of products to reactants. All right. So the K in an equilibrium expression is called the equilibrium constant, so we already saw that. Now, as long as the temperature does not change, K has a constant value because none of the concentrations used to express it change with time once equilibrium is established. So these are actually constants you can look up in a textbook because they don't change unless you change the temperature. Remember, last time we saw that temperature can increase a reaction rate, and that could cause a change in the equilibrium ratio between products and reactants. So let's talk about the relative values of this equilibrium constant and what that means. So again, remember K is a ratio of products to reactants. So if we have a relatively large value of K, then that indicates that we have a lot of products. So the equilibrium position is toward the right, or product side of the equilibrium equation. And then let's say we have a small value of K. That means we have a ton of reactants, which are in the denominator. So that indicates an equilibrium position toward the left, or reactant side. So we can use K to determine which side of a reaction is favored. So let's actually write down if K is greater than 1, so K is really large, then products are favored. Or you could also say the forward reaction is favored. Now, if K is less than 1, then reactants are favored. Or you could say the reverse reaction is favored. And then if K is equal to 1, that means the concentration of the products is equal to the concentration of the reactants. So neither side is favored. Okay. So let's talk about some factors that can influence the position of equilibrium. Because once a reaction has gotten to its equilibrium point, you could manipulate that chemical equation or that reaction. So maybe you reach equilibrium and you decide, I don't have quite enough product. I want the forward reaction to keep going. You could do a few things to make the forward reaction continue, even though you've reached equilibrium. Or maybe a reaction favors products, but you want more reactants. You could try to manipulate the reaction to favor reactants over products. So all of this has to do with something called Le Chatelier's principle. It's kind of a hard name to pronounce, Le Chatelier, obviously French. So according to Le Chatelier's principle, the position of equilibrium shifts in response to changes made in the equilibrium. So the factors that we can change are the concentrations of reactants and products, the reaction temperature, and then catalysts. So these are some things that we already talked about when we talked about how to change reaction rate. So in general, Le Chatelier's principle predicts a shift away from the side to which something is added and toward the side from which something is removed. So let's go over a few examples so we can see what that means. All right, so let's write out a generic reaction. So let's say A plus B becomes C plus D, and we can also have the reverse reaction. Now let's say that we add more reactants. So let's say we add, I'll write down here, add A and B. So we're just adding more reactants in. That means we have more collisions that can occur between the reactants. So that means we can produce more products. So if we add more reactants, the position of equilibrium will shift toward the products. So we're going to produce more products. Now, what if instead of adding more reactants, what if we remove some of the reactants? So what if on, went too far. So what if on the left-hand side we remove some A and B? That means that the equilibrium has been disrupted. Now, reactions want to always get back to equilibrium. So they're always trying to find that happy spot where the rates of the forward and the reverse reactions are the same. They're also trying to maintain this value of K where the concentration of products over reactants is a constant. So let's say we remove some of the reactants. That's going to change our ratio of products to reactants. So in order to get back to our equilibrium ratio, some of the products are going to try to reform the reactants so that they can reestablish equilibrium. So that again has to do with that last statement that we saw, where in general, Le Chatelier's principle predicts a shift away from the side to which something is added and toward the side from which something is removed. So we just saw that if we remove some of the reactants, the products want to reform some reactants. So the reaction's shifting back over to the left. Okay. Now, what if we focus on the products? It's the same exact thing. So let's say we add some more products. So we add some more C and D. then more collisions will occur, and the position of equilibrium will shift towards the reactants. But what if we remove some of the products? If we remove some of the products, again, we're disrupting our ratio of products to reactants. So what will end up happening is that any reactants that are still in solution, they're going to react to produce more products. So they're going to produce more products to re-establish equilibrium. All right, so this is actually something that is done in chemistry quite often. So for instance, I'm just going to erase this. Oh, I keep hitting the wrong thing. I apologize. So let's say that we perform a reaction in solution, and let's say we end up with some precipitate at the bottom. But let's say at some point the reaction stops and we no longer produce any precipitate, but we know that there are still some reactants left in solution. What we can do is remove the product, which will encourage reactants to react. So more product will form. So this is one way that you can manipulate a reaction to kind of get what you want. For instance, let's say the percent yield of this reaction is only 20%. So you're only producing 20% of the product that you could produce. That could be because of the equilibrium that is established in solution. So again, what you might do is set up a way to remove the product as the reaction proceeds. And remember, reactions are constantly trying to achieve that equilibrium state, or that ratio of products to reactants. So as you remove product, reactants will keep reacting to try to get to that equilibrium state. And so you can actually produce more product than you would normally expect if you just left it alone. So chemists are pretty sneaky that way. They have these little tricks they can use to manipulate reactions and get what they need. All right, so let's talk about temperature and how that affects the position of equilibrium. All right, so what if we add heat to a reaction? Remember, we have two different types of reactions, endothermic and exothermic. So let's say that A plus B plus heat becomes C plus D. And then let's say we have a different reaction where A plus B produces C plus D plus heat. So is the top reaction endothermic or exothermic? So is heat being absorbed or released? So heat is listed as a reactant, so heat is being absorbed, which means it is endothermic. And then the second reaction, heat is listed as a product. So is heat released or absorbed? It's released. So is it endothermic or exothermic? Exothermic. Okay, so let's say we have an endothermic reaction, so our first reaction here. So again, heat is a reactant, and if we increase the amount of heat, then that means that we're also increasing the amount of reactants, because technically heat is a reactant. And remember, if we increase the amount of reactants, then equilibrium will shift to the right towards products. So if we increase the heat for an endothermic reaction, then the position of equilibrium will shift toward the products. Now, what if we have a exothermic reaction? So again, we said heat is a product, and if we increase the amount of heat, then the reaction will shift toward the opposite side, so toward the reactants. Oh, and I forgot to draw my double arrows. I just drew single arrows. So these are reversible. So again, if heat is a product and we add more products, then the reaction will shift back toward reactants, so we can reestablish equilibrium. Now, what if we remove heat? So what if we put our solution or our reaction mixture in a bucket of ice? What would happen? So again, if we have our endothermic reaction, and let's say we remove heat, then we're removing a reactant. So the products will naturally want to replace that reactant we lost so we can reestablish equilibrium. So if the reaction is endothermic and we remove heat, then the position of equilibrium will shift toward the reactants. Now, if the reaction is exothermic, so heat is a product, and we remove the heat, oh, someone's at the door, then the position will shift in the opposite direction. So we're removing a product, and we want to produce more product. So the position of equilibrium will shift towards the products. Okay. Now, the last factor that can influence the position of equilibrium is a catalyst. So a catalyst cannot change the position of equilibrium. So remember, catalysts just provide a different way for reactants to react, and it lowers the energy barrier for the reaction. So if we draw our energy diagram, let's say the original activation energy is quite high, but if we add a catalyst, it becomes much lower. So this is our catalyzed pathway. All right, so the catalyst not only speeds up the forward reaction, but it can also speed up the reverse reaction, and it does so equally. So catalysts do not change the position of equilibrium, unfortunately. So if you add a catalyst to your reaction mixture, it could speed up the rate of a reaction, but it doesn't change the equilibrium of the system. So let's look at an example problem for Le Chatelier's principle. So let's say we have a reaction between 4 moles of nitrogen dioxide and 6 moles of water as a gas. And then we also have to add heat. So this is endothermic. And then let's say we produce 7 moles of oxygen and 4 moles of NH3, which is ammonia. So remember, because this is endothermic, heat is listed as a reactant. So what if we heat this reaction? So we're adding heat. that means that we're adding a reactant. So what would happen? Which position would the equilibrium shift towards? Would it go towards the left or towards the right? So if we're adding a more reactant, so more heat, that means this would shift to the right. So towards products. Now, what if we added more nitrogen dioxide, or NO2? So is NO2 a reactant or a product? It's a reactant. So we're adding reactant. So which way would this reaction shift? Would it shift towards the left or towards the right? Towards the right. Now, what if we removed some NH3? So is NH3 a reactant or a product? It's a product. So we're removing product. So would this position shift to the left or to the right? So we would want to replace that product, right? So the reaction will shift to the right again. And then what if we add a catalyst? What would happen to the equilibrium position? Nothing. Remember, we said that catalysts will affect the forward and reverse reactions equally. So nothing happens to equilibrium. Okay, and here is a solution slide for you. And that wraps up chapter 8. So this was a bit of a shorter chapter for us. We're going to move on to chapter 9, and I will see you in the next video.